Draw the moment diagrams for the frame. Assume the frame has been connected at A, B, and C. To solve this problem, first of all, let's convert our uniform distributed load into point loads. For our first load, the triangular load, it's going to be 0.5 times 4 times 6. And this comes up to be 12 kilonewton and be 2 meters away from C. Then the other load is at an angle, and it's going to be, first of all, we need to determine the length of A and B, which we can find through Pythagoras theorems. It's going to be square root of 3 squared plus 4 squared. Comes up to be 5. So now it's going to be 5 times 6, which is 30 kilonewton. And it's 2.5 meters away from each. Now, because I like everything in 90-degree order, I'm gonna find the horizontal and vertical component of this vector. So the horizontal component for this vector is going to be 30 times 3 over 5, and the vertical is going to be 4 over 5. Now we can start solving for this. We're gonna begin with section BC. So let's draw its free body diagram. For point C, we're gonna have both horizontal and vertical reaction. So is for B and C. Pardon me, B. C we have already done. And then we have our point load, which is 12 kilonewton. That's 2 meters away from C. Now we can take a moment about the point C in order to find our solution for By. So we're going to have counterclockwise 12 kilonewton, 2 meters away. Then we have clockwise By 6 meters away, all equals to 0. Solving for By, we get a solution as 4 kilonewton positive. Now we can sum the forces in y direction to find a solution for Cy. So it's going to be 12 kilonewton negative positive By, which is 4 kilonewton, and positive Cy, all equals to 0. Solving for Cy, we get our solution as 8 kilonewton. Now we can proceed to before we proceed to that, we need to find our action for Bx and Cy, which we can find through summing the forces in x fraction. So we're going to have positive Bx and negative Cy equals to 0, Cx equal to 0. This will be our equation 1, because right now we don't know how much horizontal force is being exerted by member AB. And now we can proceed with member AB. For member AB, we're going to have By, which we have found already. It's 4 kilonewton. Bx we don't know yet. And we have horizontal and vertical component, which we already found for the uniform distributed load, or the point load from the uniform distributed load. And then we have unknown Ay and Ax. Now we can sum the forces in y direction to find our solution for Ay, which is pretty simple. We can have negative 4 kilonewton, negative 24 kilonewton, and then positive Ay equals to 0. Solving for Ay, we're going to have our solution as... Now, I just noticed one thing when I was doing this. We assumed our vector direction to be wrong here. Ay is actually 18, and x direction is actually 24 kilonewton. Alright, so continuing, we're just going to have one small change here. So where we had 24, it's going to be 18. And we had 18, it's going to be 24 kilonewton in our free body diagram. and rest is as usual. Okay, so and just solving for finally for our y-axis or vertical direction. At point A, you're gonna have our AY as 22 kilonewton. Now we're going to do the same thing for x-axis. And for the x-axis, we have positive AX, positive 24 kilonewton, and then negative BX equals to 0. This will be our equation number 2. Now we can take a moment about the point A. Find our solution for BX. So we can have 24 kilonewton clockwise, and it's 2 meters away. Then we have our clockwise 18 kilonewton, and it's 1.5 meters away. Then we have our BY, which is 4 kilonewton, and it's clockwise, and it's 3 meters away. And finally, we have our BX, which is counterclockwise, and it's 4 meters away, all equals to 0. Solving for BX, we get our solution as 21.75 kilonewton. Now that we have found our BX, we can go back to our equation number 2 and plug the value of BX. And we're going to have our solution for AX as 2.25 kilonewton. Similarly, for equation 1, our CX is going to be equal to 21.75 kilonewton. And with that, now we can move forward with our shear diagram. For our shear diagram for member BC, we're going to begin with BY, which is 4 kilonewton in the positive direction, so 4 kilonewton. And then we have a triangular distributed load. That means we're going to have second order curve for our load here. And we're going to go 12 meters or 12 kilonewtons downwards over the distance of 6 kilometers or 6 meters. And our curve is going to look something like this, where it's pointing or concaving downwards because it's negative increasing. And then we have a external reaction force of Cy, which is 8, and we're going to go up 8 to 0. Now, before we proceed to movement, we need to determine our point of intersection for this curve. And we're going to try to use the easiest method this time. So we're going to determine the load equation, which we already know it's going to be negative 4x, or another way is the slope. The slope is 4 divided by 6, and solving this further or simplifying it further, going to be 2 over 3 times x. Now we can integrate this to find our shear equation, which is going to be negative x squared divided by 3 plus our constant. To find our constant, we know shear is 4 when x is 0. Therefore, our C is 4. Now we can use this value to find our value of the x. So we're going to have negative x squared divided by 3 plus 4. And for the x, we get our solution as 3.46 meters. So this is at 3.46 meters. Now we can proceed with our moment diagram. For our moment diagram, we don't have any moment at B or C. probably beginning from B, and it's going to be 0, and then at 3.46 mark, our moment's going to be the highest or the max point. And our curve is going to be concaving downwards, and it's going to be third order curve. And then at 6 meters mark, our curve is going to concave downwards again, and it's going to be third degree or third order. Now to find our max, there are two ways. We can either take the area of the curve under the positive area, or we could use our moment equation. And for this equation or this problem or this part of the problem, I'm going to just use the graphical method, which is just take the area under the curve. So our curve is second order at the shear, so it's going to be 2 divided by 3 times b, which is 3.46, times h, which is 4, and solving this we get our solution as 9.24 kilonewton meter. To find our initial vector for a, we're going to name it a prime, and b prime, we need to find their projections. Projection for a prime will be ay times cos 53.13 degrees, take away ax times sine 53.13 degrees. Our ay is 22 kilonewton, and our ax is 2.25 kilonewton. On this we get our solution as 15. Similarly, we have to find our solution for by, and it's going to be by at 53.13 degrees and bx at sine 53.13 degrees. On this we also get 15 kilonewton as a solution. Now we can start our shear diagram. And then after beginning at 15, we can go 30 points down, which will take us to negative 15. And then we know our b vector is going upwards, which will bring our shear slope to 0. Similarly, for our moment, well, before we do our moment, we need to find our intersection for the shear diagram so that we find our highest point for the moment. So for this, we know our lower equation is simply negative 6. Our shear equation is going to be negative 6 plus c. We know our shear is 15 when x is 0, so our c is 0. Now we just solve for our value of dx to find our intersect. And in this case, it's going to be 15 divided by 6, which is 2.5. So this is at 2.5 meters. Now we can begin our moment, and looking at our section AB, we know there is no moment at A, so therefore we're going to begin at 0, and then at 2.5 is where we're going to have our highest or max moment. And our max moment is simply the area of the positive triangle from the shear diagram. So it's going to be 15 times 2.5 times 0.5, which is 18.75. And it's going to be concaving downward because we have positive decreasing. And then this moment is going to go all the way to 0 until we had the length of the beam as 5, so until 5 meters. And it's going to be concaving downwards as well.